Okay, so thanks for sticking around, guys. Really appreciate it. Last lecture we did a lot of derivations, but we did very few examples. So before we move to a new topic, I think it's good to look at an example. And the example we're going to look at is something that's very commonly used, and it's called inductive degeneration. If you look at RF amplifiers, you'll often see a basic building block, which is this. So it's our basic transistor, but it uses an L as a degeneration. So this is a series feedback, series with the input, series with the output. And so the question is, first of all, what's the effect of doing series feedback? What are some of the benefits? We'll see that throughout our analysis. Now, if I have a circuit that uses series feedback, what's the best two-port representation? That's right, Z matrix. So let's calculate the Z matrix. So let's start out with the Z matrix for a FET. So I'll call that Z FET. And basically this is the Z matrix for, I'm going to use a very simple model. I'm just going to use this model, as simple as it can get. So Z11 is the input impedance with the output open circuited, right? So it's just 1 over j omega CGS. Okay? Z12 is 0, right? Because there's no feedback. Okay? Z21 is the output voltage when we apply an input. So let me calculate Z21. So basically V2 is Z21I1 plus Z22I2. So I'm going to open circuit the output and drive a current I1 into port 1, let's say of 1 amp, and simply calculate the output. Well, the output V2 is simply GMRO divided by j omega CGS. So minus, right? So Z21 is minus GMRO divided by j omega CGS. And finally, what's Z22? Well, Z22 is looking out here when the input is open circuited, so it's just RO. So this is our extremely simple transistor model, and I'm using it to keep the calculations as simple as we can. It turns out this is enough to really explain the important salient features of inductive degeneration. Okay? Pretty simple. Well, what about for series feedback? What's the Z matrix for this trivial circuit? This is port 1, this is port 2. The Z matrix for the feedback is just j omega ls, let's call this ls, 1, 1, 1. Okay? And I won't bother to derive it because it's so trivial. I leave that to you. So the Z matrix for the total amplifier is the Z matrix of the FET plus the Z matrix of the feedback. And so we can all add in this class hopefully, Z11, Z12, and notice that the series feedback actually introduced feedback, I should say. It introduced feedback. Without LS, Z12 was equal to 0, but now because of the feedback we have a finite amount of Z12. And this again is something that you should, whenever you see a circuit that doesn't have feedback to begin with, and you do something to it that introduces feedback, you should worry about stability, especially at high frequencies. So just adding this element here clearly introduces a Z12 factor, because now part of the output voltage appears at the input. The output current generates an input voltage. Okay? So this is the overall Z matrix of the system. And one thing that I claimed, I haven't proven this, but you can take to be true, is that all the equations we derived up to here for Z, for gain, for stability factor, Z input impedance, output impedance, they all are the same no matter what parameters you're using. So in particular, if we take the definition of K and we plug in, see if I have the K written down here. So K is 2 times the real part of Z11, real part of Z22, minus the real part of Z12, Z21, divided by the magnitude of Z12, Z21. Okay? And now if I substitute, I have 2 times the real part of Z11, which is 0, times the real part of Z22, which is RO, minus the real part of the product Z12, Z21. So if I multiply this out, you can see the first term is certainly real, because I have J squared, which gives me minus omega squared LS squared. And the second term also is real, because the J omega cancels out. So the second term gives me minus GM ROLS divided by CGS. And then on the denominator, I have the magnitude of this product. So it's basically the real part squared plus the imaginary part squared. In this case, if I multiply it out, it's all real. And I think I made a mistake in my notes. Whoops. Okay. So if we multiply this out, it's omega squared LS squared. Yeah, it's actually, yeah, never mind. There's no mistake here. Sorry. This is what happens when you lecture twice in a row. Your mind gets to go numb a little bit. Okay, so it's just the magnitude of this product, and that's what the magnitude of the product is. Okay? So that's our K factor. And what we'd like to see is under what conditions is K greater than 1? Well, take a look. If I, now this term is all 0 here, and this term becomes plus, and so now we see this ratio is exactly equal to 1. So this is unconditionally stable. That's actually pretty nice. It took our device, which was already unconditionally stable. We introduced feedback, but we found that this feedback could never make it actually oscillate. It's always going to be stable. So now if we look at the expression for the maximum gain we can get from this device, now I'm using Z parameters. It's Z21 over Z12, K minus K squared minus 1. Well, K is always equal to 1 for this amplifier, so it's just Z21 over Z12. And Z21 we found, this is Z21 magnitude, and this is Z12. So if I just substitute here, sorry I can't show both. Maybe I can try. Yeah. So Z21 magnitude is omega LS plus GMRO omega CGS over omega LS. And if I simplify this, this turns out to be 1 plus GMRO divided by omega squared LS CGS. And I can substitute for GM over CGS, so I can write this as 1 plus omega T over omega naught squared divided by RO over omega T LS. Okay? So this is the maximum gain I can get out of this device. It's basically a ratio of the omega t of the device and the operating frequency, and a ratio between R naught and a resistance equal to omega t Ls. Now remember omega t Ls because it's going to be an important, what we're going to show is this is actually equal to the real part of Z in. Okay? And we know that we get maximum gain when we impedance match, and so this is actually going to equal to Rs, the source resistance. Okay? Any questions about this this calculation? All right, so let's show that this in fact is equal to the source resistance. Let me look at Z in. So Z in is the real part of Z11, right? And again, if I go back and look at my Z matrix, sorry, what am I saying? Z in is Z11 minus Z12 Z21 divided by Z22 plus ZL. Okay, so now if I go back and look at this matrix, I can just substitute here. So Z11 is J omega Ls plus 1 over J omega CGS minus Z12, which is J omega Ls. Z21 is J omega Ls minus GM RO divided by J omega CGS divided by Z22, which is RO plus J omega Ls plus ZL. Okay? So now let me find the real and imaginary part of this expression. Let me focus in on this term here. Let's assume that at the operating frequency RO dominates this expression. Okay? That's reasonable, right? Because LS, you'll have to trust me on this one, LS turns out to be a pretty small inductance. And let's say ZL is like 50 ohms or something like that. And let's say RO is a few hundred ohms, 500 ohms or something. Is there a question? No. Okay, good. Okay, so if I now multiply this numerator out again, I'll have omega squared Ls squared plus GM RO Ls divided by CGS, all divided by RO. So I'm looking at the real part of Z in, and I'm claiming that it's approximately equal to this divided by just RO. Okay? And so continuing here, I have another term that looks like that. So I'm dividing by RO cancels out, and so I can write this as omega squared Ls squared divided by RO plus omega t times Ls. Okay? And again, if I assume RO is sufficiently large, then we can say that this term will dominate. So I can write this as omega t Ls 1 plus omega t omega, sorry, if I just assume that this is much larger than this, then this term will actually dominate. And so the real part of Z in is approximately omega t Ls. Okay? Now, we'll look back to the equation we derived here. Here, I said that this is approximately the real part of Z in, which for an impedance match condition is just Rs. And so now you see that the power gain is proportional to omega t over omega naught squared times the ratio of the output resistance to Rs. Okay? Well, that's interesting. In fact, this is the reason that we use inductive degeneration. The reason we use inductive degeneration is to synthesize a real input impedance. So if I take my capacitor, if I take my transistor and I look into Z in, the real part of Z in is just RG, which is pretty small. And let's say I want to drive this with a 50 ohm source resistance, right? Let's say I have a cable or a transmission line which is, let's say, has a Z naught of 50 ohms, and I want my transistor to terminate this with 50 ohms. Well, that's pretty hard to do with the transistor. Transistor on its own is going to look like a capacitive termination. Another way to look at it is if I want to extract the maximum power gain of this transistor, I want to drive it with a source impedance, which is the complex conjugate of the input impedance. Well, RG is the real part of the input impedance, which is very small. It might not be possible to drive it with a source that has such a small, let's say this is 1 ohm. It might not be possible to drive it with a 1 ohm source. So inductive degeneration lets you raise the input impedance to any value that you want. So this is LS. Now looking into here, the real part of Zn is approximately omega t Ls. So I can make Ls large enough so that this product is exactly equal to Rs, or let's say Z naught in the case of a transmission line. Okay. Now we're going to talk more about designing amplifiers that provide an input match, but this is kind of a preview of what we're going to do. Okay. Questions or comments? Okay. Well, if you go back and look at this equation, you might comment that, sure, you know, you've matched, this is the real part, you've been able to match that correctly. Well, what about the imaginary part? There's still this residual imaginary part. You're right. We basically, if we pick LS to provide an input match, it will not necessarily resonate with this CGS. So what we can do is introduce another inductance here, so that now this inductance plus this inductance resonates the input capacitance. And so this now looks like a series resonant circuit at the input. All right? Okay, so we analyzed the problem using series feedback. Now I encourage you to go and analyze a problem with shunt feedback. And use the Y matrix, use all the equations that we've derived, and try to derive the maximum gain you can get with shunt feedback, derive under what conditions shunt feedback is stable, and so on and so forth. Okay? So that's a follow-up to homework number 1. Maybe it's a good first problem for homework number 2. Okay, we're going to start a new topic now. Before I do that, take any more questions. All right, so the new topic is impedance matching. And again, it's very related to resonance. So if you had trouble with the resonance lecture, this is a good time to go review before you start this lecture. So first of all, what is impedance matching? Well, we alluded to it before. Impedance matching, I have my 2-port, and usually I don't actually control my source and load resistance. They're kind of given to me. For instance, this might be an antenna, and the person who designed the antenna says, well, the best antenna that when I design my antenna, the best I get is 300 ohms. So your source impedance has to be 300 ohms. And you say, well, actually, I want a 10 ohms. I kind of want to be driven by 10 ohms because that gives me better power gain. And the antenna designer says, tough. So what do? You actually design a matching network. So we'll call this M1 that transforms RS into, let's say, RS opt. Or more generally, transforms ZS into ZS opt. Likewise, your load may be a cable, which is 75 ohms. And so let's say to get the most power gain, you want 200 ohms. So again, you have to put in a matching network, M2, to synthesize the RL opt that you would like. Now, when we studied the 2 ports, we found ZS opt ZL opt to maximize, let's say, GT, the transducer gain. How about other cases? Why else would you want to provide an impedance match? Can someone think of other situations where an impedance match may be useful? So in essence, this is kind of the knob that we were talking about. This is the ability to tune the source and load to get the maximum gain. In practice, this is how we do it. We can't really change the source and load, but we can design matching networks around our device. But what are some other reasons why we'd like to play the matchmaker, if you will? So the question is, why match? So already we see that we get the maximum power gain. Any other reasons?
Yeah, to prevent reflections from the line, to make a...
Very good. To prevent reflections, and this is something that was brought up a couple lectures ago as well. And there are many situations where you'd like to prevent reflections. Let's talk about a simple one. Let's say you have an antenna on your roof of your house, and you have this long cable, and that comes into your house, and let's say this goes into your TV. So let's say this is plugged into your television, and you're watching, let's say, a sports game or something on the television, and let's say that your television, and let's assume this cable Z0, and this antenna impedance is also Z0. Let's assume that the input impedance, so let's, okay, I'm going to make an example here, but this is not Z0 to make this meaningful. Let's say that Zin of your television is also not equal to Z0. Let's say this is a 75 ohm cable, and let's say that your television is designed for 50 ohms. Okay, let's just say the designer made a mistake. What's the big deal? Well, the big deal, first of all, is you're not going to transfer the maximum power. That we've already talked about. But the other problem is that you're going to get reflections. So the signal that comes in, the reason you don't get maximum power is that power is reflected from this television. And this is something we study in 117 when we study transmission lines. And this reflected power is going to come back to the antenna, and if the antenna is also mismatched, it's going to reflect again. So when the new signal arrives, what does it look like on the screen? It's a ghost, right? So what you'll notice, because there's a time delay between the input, the real signal, and the reflection, you actually see a ghost. And since there's multiple reflections, you might see multiple ghosts, or you might see a fuzzy ghost. Go try this at home. It's kind of neat. You know, introduce a mismatch and, you know, watch what happens on the screen. Another example is a data communication system. If I'm sending high-speed bits and I have an amplifier, so let's say I have a high-speed link, and let's say I have an amplifier at the end of the link. If the input impedance is not equal to Z0, then what happens is this data gets reflected and actually produces intersymbol interference. So it gets harder and harder to correctly detect these bits. Okay? So there are many situations where we terminate to prevent reflections. And what's a big difference between case 1 and case 2 is we really would like broadband matching. In other words, in this case, for instance, this data signal is broadband, it's high speed. So we really would like to provide a termination from DC all the way out to, let's say, a few gigahertz, if this is a gigabit per second kind of link. Whereas here, for the television signal, maybe if we're just watching one channel, we could stand a narrowband match. But if you want all your television channels to look equally as good, you want a broadband match. So there are cases where we just care about one frequency, kind of like maximizing the gain of a narrowband amplifier, and there are other cases where we'd like to get a broadband match. Okay, very good. Any other places where maybe matching may help? For radar systems? Yeah, let's stop with reflection. Let's think of other reasons why we might want to match. Well, we haven't talked about it yet, but in this class we're going to spend a lot of time talking about noise. And when you design amplifiers, generally you want to design an amplifier that introduces as little noise into our system as possible. And it turns out that you can, I won't go through the details, but let's just say that there is an optimum source impedance that minimizes the noise contribution of a two-port. And in fact, this optimum impedance is not necessarily the same as the optimal impedance for maximum power gain. So in some cases you have to make a compromise and ask yourself, do I want to match for gain or do I want to match for noise? And so that's another reason that we would impedance match. And we'll go into this in a lot of detail later in the course. How about a final reason that I can think of before we actually start looking at matching networks? Why else? Well, efficiency. It turns out that a lot of times power gain is not so important as power efficiency. A good example of that is a power amplifier, let's say sitting in your pocket transmitting data on your cell phone. Turns out that this power amplifier is probably the dominant power consumer in, let's say, a mobile communication device. And you might be able to give up power gain. So let's say the power gain is how much input power you put in versus output power, if you can improve the efficiency. Now the efficiency is the power, let's say, that we radiate versus the total power consumption in the system. And what we'll find in this course is, again, there is an RL optimum that maximizes efficiency. And so for when you design power amplifiers, we won't be concerned with power gain, we'll be concerned with efficiency. So these are some 4 important reasons why we should care about impedance matching. Okay. All right, so how do we build impedance matching networks? So the simplest impedance matching networks are capacitive and inductive dividers. And the idea is let's say this is RL. What's the input impedance looking into this network? Well, this is a very simple circuit. Let's say this is C1, C2. We could analyze it completely and come out with an expression, but let's just come out with an approximate expression. Let's assume that the reactances XC1 and XC2 are less, let's say much less, than RL. That means that if I put in a voltage source here, most of the current actually will flow through here. Some small part of it will go through here, but just to make the analysis very simple, let's neglect that. Well, if that's the case, then this is simply a capacitive voltage divider, right? So if I call this Vout, Vout is equal to C1 over C1 plus C2 Vs, right? And I can say that this is Vs over N. If I do anytime I do a voltage transformation, I also do a current transformation. Let me just review that with you guys. Let's assume that I have a lossless two-port. And this is V1 and this is V2, I1, I2. And let me assume that V2 is 1 over N times V1, right? This could be a transformer, for instance. Well, because it's lossless, that implies that V1 I1 has to equal to V2 I2, right? Actually, I2 is defined in this direction. It's the current going into the two ports. So whatever power I put in should equal minus the power I take out, because it's lossless. That means if there's voltage gain, then the current gain should be the opposite of the voltage gain, right? So for our voltage divider, you might expect that because the output voltage is n times smaller than the input voltage, then the output current should be n times larger. So if I look at V out over I out, that's simply equal to RL. Redraw that here. But substituting here, it's equal to Vs over N times N Is. In other words, it's 1 over N squared Vs Is. So Vs over Is is N squared times RL. So neglecting, basically just looking at the real part of the current that flows, we see that this voltage divider boosts this resistance up by a factor of N squared. Now remember, we started out by saying the capacitance part actually dominates. So really, Zin looks like the series capacitors, so it's 1 over j omega C1 C2 series combination. This is the operator, not necessarily two caps in parallel, plus N squared times RL. Okay? And this is kind of inconvenient, right? Unless these capacitors are really small, this is inconvenient, so we could always tune this out by putting a big capacitor here, big inductor here, to tune out that part. So this is a very simple way to build a impedance matching network. It's particularly nice for integrated circuits because it just involves using capacitors and possibly an inductor if we don't like this capacitive part to load us down. And it lets us go from, let's say, small resistance to a large resistance or vice versa. Okay. Now I can do the same thing with inductors. I can have an inductive divider and then use a capacitor to tune out the inductive part. Same basic idea. So this is called an inductive voltage divider. Now in the notes, I actually have this is the second part of the chapter that I told you guys about last lecture. There's a more detailed analysis of the circuit, but at the end of the day, the results kind of match our intuition. Okay, and let's not forget our old favorite way of doing impedance matching. We could also use transformers, right? This is an n-to-1 transformer. The very name transformer comes about because it can transform voltages and currents, and therefore transform impedances. We'll talk a lot more about real transformers later in the class, because unfortunately, anytime you build a transformer, it doesn't really look like this. It's a lot more complicated. But for now, let's just say that this is also an option for doing impedance matching. Okay? Questions or comments? All right, so what we're going to do is focus on some other impedance matching networks. First one we'll look at is called an L matching network. Okay? And the idea behind an L matching network is as follows. So first, let's see how it works. Let's just look at a particular example. It's called an L matching network because it looks like an L, right? There's our L. And what I'm going to do is hook up an RL here, and then I'm going to look at Zin to see what happens at resonance in this circuit. Okay? And I'm going to make use of a transformation I introduced last lecture. Remember last lecture we saw that at any given particular frequency, if we have an X and an R, let's call this JX and an R, and we can define the series Q as X over R, then this is equivalent to JX prime and R prime, and we found that R prime is 1 plus Q squared times R, and X prime is 1 plus Q to the minus 2 times X. Okay? So now if we look at this circuit here, we can see that it would be really nice to analyze this. If I want to find Z in, it would be really nice if I could make this a parallel RLC circuit, and then I could make, if I want to synthesize a real input impedance, I can make the L and C resonate, and I'm just left with the parallel R. So let me transform this into this circuit. So this will be RL prime, this will be L prime, and then this will be C. Okay? And if I just apply this formula, then RL prime is equal to 1 plus Q squared times RL, where Q is omega L over RL. Okay. L prime is 1 plus Q to the minus 2 times L, which is approximately L if the quality factor is, let's say, larger than 4 or 5. If not, we should account for how much L changes. So now, from the generator side, I have some source impedance RS, and I've connected my L network. From the source's perspective, what I've done is I've transformed my circuit into the following parallel RLC circuit. This is 1 plus Q squared RL, this is RS, this is C, this is L prime, and therefore I will pick C to resonate with L, and so then the equivalent circuit breaks down into this simple form. It's just a voltage divider, right? That clear? Any questions? So now if I want an impedance match, I would set RS equal to RL 1 plus Q squared. Now this RS may equal the RS of the source, or it may be equal to basically the optimum source impedance or the optimum load, so on and so forth. So it's not necessarily a match to the same impedance, it's a match to the impedance that you'd like to see. Okay? So if I solve this equation, remember RS and RL are usually given. I can see that I can now solve for Q as RS over RL minus 1. And because Q has to be positive, that means that RS has to be bigger than RL. So this circuit will transform a low impedance to a high impedance. In other words, if I redraw this, this is R low. The action of this L matching network is to transform this up so that from here I see R high. Okay? And what's really interesting is that the quality factor of this network, assuming I use ideal components, the quality factor is determined by the transformation ratio. So let's do a very, very simple example. Let's say that R high is 100 ohms and R low is 10 ohms. So I have 10 ohms, but I really would like to drive it with 100 ohms. Now, if I drive it directly, I'm going to waste a lot of power. I'm not going to be able to transfer the maximum power to the load. So what I'm going to do is I'm going to put a matching network in here to make this 100 ohms, and then I extract the most power possible. I extract the available power. Well, the design equations are that the Q of the matching network therefore is R high over R low minus 1, or 10 minus 1 is 9, square root is 3. So the network Q is fixed at 3 based on this impedance matching network. Okay? Now what's interesting is this is the network Q. This is the Q of the overall circuit. It has nothing to do with the component Qs. Up to here, we're assuming our components are ideal. We'll come back and look at what happens when we have non-ideal components. But for now, let's just keep it ideal. The other thing that you might object to is, why did I put the L here and the C here? Is there any reason to do that? Actually, no. This would work for any combination of reactances as long as at the end of the day I can resonate out the resulting reactances. So in fact, I could put a capacitor here and the inductor here. This is also an L matching network. And the design equations are identical. Okay? So what are the design equations? Well, let's finish this example. If Q is equal to 3, remember Q is this guy. Let's call this X series. Let's call this X parallel. The Q is XS over RL, or RL is 10 ohms. We know the Q, that means XS should be 30 ohms. So for instance, I can make this plus JXS, or I can make it minus JXS. Okay? And then how do I pick XP? XP should equal minus XS prime, where XS prime is 1 plus 1/9 times 30 ohms. So it's about 10% larger, about 32, 33 ohms. Okay? So if this is a capacitor, this is an inductor. If this is an inductor, this is a capacitor. All right? Is that pretty clear? Question?
Yeah, so the Q here, does it provide any information about the bandwidth of the matching as well?
It does. Actually, the Q tells us how good the matching bandwidth is going to be, and already we see a problem because we had no way of controlling Q. Q just comes out of the calculations. It's determined by the ratio of impedance transformation. So here a Q of 3 is pretty wide band, right? But what if we wanted to go from 1 ohm to 100 ohms? Then our Q factor would be much larger, right? And then the circuit would be much more narrow band. So the higher the transformation ratio, the more narrow band we end up with a solution. And that's a problem. In many cases we want to be able to control the bandwidth, either to make it more narrow band or less narrow band, as we'll see. We'll come back to that issue later in the lecture. Okay, well, this is a nice way of taking a low impedance and making it high impedance. What about the reverse process? How do I make a high impedance a low impedance? Any guesses? Yeah, the other way around, right? In fact, this is a symmetric network, right? It transforms 10 ohms to 100 ohms. But if I look here, it also transforms 100 ohms into 10 ohms, right? That should be obvious from power matching theorem. If I'm extracting the optimum power at this point, since this is lossless, I must be also extracting the optimum power at this point. So if I just flip this around, it does the opposite thing. So what does it look like if I flip it around? This is, let's say now it's R high. I connect first, so now I connect my L matching network in this direction. And now, same formulas apply. R low is equal to R high divided by 1 plus Q squared. Okay? Let's just review how we get that. Let's call this XP. Now let's do a parallel to series transformation. So this, we're going to transform let's call this XS, this is XS, this is XP prime, and this is R high prime. Okay? And of course, we set these equal to each other and with negative signs so that they resonate out, and we just end up with R high prime. Now remember, XP, the Q for a parallel network is R high over XP, right? And when we do this transformation, we know that this is satisfied. This is the part of the transformation. And now XP prime is equal to XP 1 plus Q minus 2. Again, using the same formula as before, which again is approximately XP for a high Q circuit. So the only thing that changes in the design of high to low is basically if you just remember this equation, it's always valid. And the easy way to remember it is if I put my L network with this shunt element in parallel, it reduces the impedance. If I put it in series, it brings it up. So you can remember which way to hook up your L matching networks. Okay? I think I have a little table in here that we could look at. This is from the chapter that you guys have online. So here, starting out here, we see RS is bigger than RL. That's why we connect the inductor in series with RL. We could also do a capacitor, right? This same thing. Or in general, we use complex reactances. This is the opposite case. We hook it up the other way around. We put it in parallel. We could use a capacitor or an inductor. And you might say, well, which one is better, right? You know, how do you decide which one to use? Should I use a capacitor first or an inductor first? Well, for one thing, these are different networks. This is a high-pass network. This is a low-pass network. So in a lot of the cases, you want to be able to isolate two stages anyway, and so why not do it automatically with the matching network? So this is very convenient if I want to isolate the DC. The opposite is true if I actually want to preserve the DC. If I want the DC value of stage 1 to be the same as the DC value of stage 2, then an inductor is very convenient. So let me draw a couple of examples where you would use one or the other. So let's say, okay, I already started drawing stuff. Let's say that looking into here, RG is very small. So I'd like to boost RG up so that it matches RO of the state. So I get an impedance match between these two amplifiers. Well, to do that, I connect a capacitance in series and an inductance to ground. Right? So this is my L matching network. And now, looking out here, I should see RO for an impedance match between these two stages. Well, this is actually very convenient because, first of all, I can now put this inductor to the power supply, and it provides a DC current for this stage. And this capacitor automatically provides AC coupling, so I can now bias this stage separately from this stage. So this is a very nice, convenient topology. Well, the downside, though, is that what if we wanted to low-pass filter the output of this guy before it drives the second stage? This is doing the opposite. It's high-pass filtering. In that case, we would use the other termination, but we'd end up having to put in a lot of extra elements. So, for instance, if I wanted to do a low-pass, do something like this, but I still need to provide DC current, so I actually need another inductor here. And now, basically, I need to provide another capacitor. So this is L infinity and this is C infinity. We call this a choke and we call this a coupling capacitor. And in practice, basically any large inductor acts like a choke, it basically doesn't upset the AC operating point because at RF frequencies it looks like a high impedance, and so it kind of disappears. Same with a capacitor. If I put a capacitor in series that's very large, high frequency, it looks like a short, so it doesn't upset anything, but it does prevent the DC operating point of this stage from interfering with the DC operating point of this stage. Question?
Would the choke be such a large capacity you want to do it off chip, or would you be able to keep it on chip?
It's a good question. You can build them on chip. In fact, in practice, you'd never would really make this very large. Much better to make this part of the tuning network that's already here. But there are certain cases where you absolutely do need a very large inductor, say to drive the tuning line of an oscillator. You can build them on chip as large as hundreds of nanohenries. So for gigahertz frequencies, that's effectively a choke. But if you're talking about megahertz frequencies, certainly it has to be off chip. You can't make them on chip. Okay, so let me give you guys a little bit of intuition for how matching networks work. I mean, up to now we just used kind of our equations, and the equations told us, yeah, it's easy. L matching network works. So let me think about this a slightly different way. If I look at this circuit here, this looks like a okay, so let me make sure that I got the intuition right before I try to give it to you guys. So this is R high, and this is going to this L matching network is going to transform this to L low. So what I'd like to do is, if I can take this voltage source and somehow boost the voltage that drives this RL. In other words, if I go back to my picture of a transformer, let's say this is 100 ohms, okay? And let's say this has a 1 to 10 turns ratio. So if I put 1 volt here, the voltage across here is 10 volts, right? And if I put 10 volts across 100 ohms, I know I get 10 milliamps of current. So the R, so if I have 10 milliamps of current flowing here, that means I have 100 milliamps flowing here. So from this point, I see 1 volt over 100 milliamps, right? And that is 10 ohms, right? That should be 1 ohm. I made a mistake. On the right, it's 100 milliamps. Let me think. 10 volts, yeah. 100 milliamps, so this is an amp. 1 amp, and so this is 1 ohm. Okay, now it's right. Thanks. So what's happened here in this circuit is the fact that I've multiplied the voltage when I've applied it across here. That did the magic trick. In this circuit, if I can think of this as a series feedback circuit, then I can also produce voltage multiplication across a reactance, right? So I know that in this circuit, if I have a series feedback circuit, then the voltage across this resistance is going to be Q times less than the voltage across this reactance. So what I really want to do is take advantage of this Q multiplying property to make this circuit work. Let me do it another way. So let me go back to this picture and let me follow my notes so I might make more sense. Okay, so in my notes I'm suggesting that we transform this into a parallel circuit. Okay, and doesn't make sense to me. Let's go back to my way. So the idea is if I transform this into a series circuit to understand what's happening, then whatever voltage I apply here at resonance gets applied here. That's not what I want. Okay, let me see. So what I want is, let's come back here. I want the voltage to get boosted. So in this circuit here, yeah, I think I was going along the right lines to begin with. So in this circuit, what happens is, if I drive this with some source resistance RS, then at resonance, if this is designed to be a matched circuit, the current is just Vs over 2Rs, right? But the voltage across the reactances is Q times Vs, right? And that means that because I have a voltage multiplication, I have the same current multiplication in the other direction. So the current that I can drive this with is 1 over Q times smaller. So the net effect is that I've increased, basically I've decreased this by a factor of Q squared. I think getting things wrong here. But the important point is that the reason an L matching network works is because it can boost voltages and currents by a factor of Q, just like our transformer does. And intuitively, though, you would say, well, if it boosts it by Q, then it should go up like Q squared, right? So if you didn't do any calculations and you said, I have a circuit that can boost the voltage by a factor of Q, therefore it should be able to boost the impedance by Q squared, or vice versa. That's pretty much what we found when we did the exact analysis. The only difference was it was 1 plus Q squared. And the reason is that we don't exactly have series and parallel circuits. They're slightly different. When you transform them, that extra factor of 1 comes into play. Sorry, I think I ended up confusing you guys and myself more than making this clear. Anyhow, it's in that chapter. You guys can read it, and it'll make more sense. Okay. So the next topic is the insertion loss of matching networks. Now, an ideal matching network, of course, doesn't have any insertion loss. It's ideal elements. But in reality, whenever I buy an inductor or build an inductor, it has finite Q. Let's call this QL and this QC. This is the quality factor of the inductor, this is the quality factor of the capacitor. And the question is, how bad is this? How much loss do I have as a result of putting it? So if I put in P in, the power going into the load is not equal to P in. The difference is dissipated as heat inside our matching network. And the reason it's important to know what the insertion loss is of a matching network is the whole point of inserting a matching network is to maximize the power transfer. But inevitably, you're going to lose some power because the finite quality factor of your matching network. So what we'd like to know is how bad is it? Because if it's bad enough, then we won't use a matching network at all. We'll just directly connect our load to our source. So I'm going to derive a really approximate expression for the insertion loss, which is more intuitive than anything. And so that the way we derive it is we, first of all, make an obvious statement. We say that the input power is equal to the power dissipated plus the power that goes to the load, right? And of course we want to minimize the power dissipated. So if we look at the insertion loss, that's the power that goes to the load divided the power going input. And so I just substitute here and just derive a very obvious expression that it's basically proportional to 1 over 1 plus power dissipated divided by the power of the load. Okay? Very obvious expression. Okay, so now to find the power dissipated, we're going to call upon, again, your background about resonant circuits. So in particular, if I have an inductor, I know an inductor stores reactive energy, magnetic energy, that goes like 1/4 Li squared, where this is the current going through the inductor. Okay? You see, I'm analyzing a particular problem here. Okay, that's actually not that important. Now, if I look at omega naught times omega m, let me write this as 1/4 Vs squared over 4Rs squared times L. That's because at resonance, the current that flows is just, this is for a series resonant circuit, is just proportional to Rs. And if I look at omega naught times omega m, I have 1/4 Vs squared over 4Rs squared, omega naught L over Rs. Well, omega naught L over Rs is just Q, so I can write this as 1/2 Vs squared over 8Rs times Q. And to first order, this is the power that's going to the load, right? Under a matched condition, this is the available power from the load. So this is 1/2 the power that goes into the load times Q. Okay? That makes sense to everybody? So let me just back up and explain the calculation here. I want to find out how much power is stored in this circuit, right? The only places I can store power is in this inductor and in this capacitor, right? So once I have current flowing in this system, I know how much current is going through this inductor, therefore I can find the magnetic energy that's stored in it. And I know at resonance, the energy stored in this inductor is the same as the energy stored in this capacitor, right? So here, I know that in resonance, the current is simply the voltage divided by 2Rs, because in a series resonant circuit, Rs and CS, LS and C, L and C cancel out. And what I notice is that I can write this as the available power, basically the power that's going to the load, times the quality factor. So all I've done is just done a little bit of manipulation to show that the power stored in an inductor is Q times larger than the power that's going into our load. Okay? And that's kind of a general statement, right? If you have an inductor, it's storing a lot more energy than it's dissipating. That's actually the definition of the quality factor. So we could come back and redefine the quality factor. In fact, the more general definition of quality factor is that quality factor, Q, is proportional to the power stored divided by the power dissipated. So this is a much more fundamental definition of quality factor. It turns out for second order circuits, these different definitions are actually equivalent. But let me not get distracted too much. So the important point is that if I look at the total stored power, at resonance, the power stored in the inductor is equal to the power stored in the capacitor. And so this factor of 1/2 goes away, and I just have Q times the power that's going into the load. Okay? So now this is the important part. By definition then, the power dissipated in our capacitor and our inductor is basically the power stored divided by the Q of those components. So it's the power dissipated is the power stored divided by the Q of the component. Okay? And so we've shown now that the power dissipated is Q times PL divided by the Q of the component. We'll just call that QC. Okay? Remember, this is the Q of the network. This is the Q of the component in question. So now if I go back to the simple expression I derived here for insertion loss, I have that P dissipation is basically Q over QC times PL. So if I substitute in here, I get a very simple expression for the insertion loss. Okay, so this is the network Q. This is the component Q. It's the net component Q because we're using both inductors and capacitors. Okay, now this is an approximation. And it's more and more valid as we go to high Q assumption, to a high Q circuit. The reason it's an assumption is I kind of made a lot of assumptions here. I first of all assumed that the biggest assumption is at this point, is assuming that the power dissipated is simply the power stored divided by the component Q. Even though this is exact, I don't really know the power that's stored that accurately. I kind of made an assumption here that this is roughly the power that's stored, because really the power that's going to the load is not really this. It's less than this, right? Because I'm dissipating some power. Just to make things convenient, I use this as the power of the load. So really this is PL minus P dissipated. So this is not really this is not equal to PL. But this is the approximation that we used. Okay? But the gist of it is that the results are actually pretty good and they're pretty insightful because they tell us that to minimize the insertion loss, use high Q components. Well, that's obvious, right? Of course, anyone could have told you that. But what's important is it's not the absolute quality factor that matters, it's the relative quality factor, relative to the network Q. So if someone tells you that, hey, I'm designing a matching network and my quality factor is 2, should I use a QC of 1,000 or should I use a QC of 100? Oh, you would say, you know what, don't spend your money on that expensive component that has a QC of 1,000 because your network quality factor is only 2. So, you know, it's not going to really matter that much. It's a marginal difference. On the other hand, if someone says that my network quality is 100 and I want to use components with a quality factor of 100, you can see right away that the insertion loss is going to be more than 50%. Right? So it really matters what network Q that you're trying to achieve. In other words, it matters what the impedance ratio is, because remember, the Q of the network for this L matching network is related to the impedance ratio square root. So the bigger the step you're trying to make in impedance, the higher your network Q is going to be, and therefore the higher the component Qs that you have to use. Okay? Now, you might also notice that up to now we have only dealt with real loads and real sources. So what if I have a complex load or a complex source? How do I handle that? So let's say that in addition to having some RL, I also have some XL. And let's say that I want to transform this into RS. And let's just say that RS is larger than RL. Okay? Can anyone think of an easy way of using our L matching network to achieve this? Give you guys a hint. It's reactance absorption. The idea is very simple. I can just connect minus XL across here. Now I just have RL. and then I just use my regular network. Right? In many cases, I can actually just absorb this into the matching network. So let's assume that RS is less than RL. So what I first do is I connect minus XL here, and then let's call this minus B because they're in parallel. So I put minus B here, cancel this out, and then I put in my XP and my XS here. And now you notice that this and this together can get absorbed together. So for instance, let me just do a real example. Let's say this is my load. And I'm going to, first of all, put a capacitor across here so that from here I just see R. And then I'm going to put another matching network here. And so here I just see an RS, which is less than RL, and I notice that this extra capacitor could just get absorbed into one capacitor. So that's why we call it reactance absorption, because a lot of times we can absorb the complex part of our load and source into the matching network itself. So even though the matching networks that we've discussed up to now, all the design equations were for real loads and real sources, you can see that it very simply generalizes to complex source and complex load. Okay? Any questions about that? Okay, so now let's come back to more complicated matching networks. Let's talk about two-stage matching networks. First of all, why do we even need another matching network? It seems like the L matching network is great, we can do everything with it. Why would we ever want to do something differently? Anybody? Bandwidth, yeah. Basically, we found that we had no control over the bandwidth of a single stage matching network. The bandwidth was set by the matching ratio. What else?
Another degree of freedom.
Another degree of freedom for what?
To design the queue, for example.
Okay, but that's bandwidth, right? Yeah. Okay, anything else? Well, how about insertion loss? Is it possible that by using more stages we can get less insertion loss? In fact, it's true, you can. And the reason is that insertion loss is really related to the network quality factor. And in certain circuits that you have extremely high network quality factors, using multiple stages can actually relax the quality factor. We'll see how that works out in a moment. Let's talk about two back-to-back L sections. So let's say that I have two L matching networks like this. So this is R high, and what I do is I can just analyze this as two cascade L matching networks, right? So in step 1, I bring this to some R intermediate, and then in step 2 I bring it to R low. So if R low is here, this is R intermediate, and this is R high. In a single matching network, I take a one jump. In a two-stage matching networks, I actually take two steps. And now you see that that extra degree of freedom is Ri. I can choose any intermediate Ri between R low and R high, and this circuit still works, right? So this introduces 1 degree of freedom. Do you think this will have a higher quality factor? Just if you had to guess, would the quality of this matching network be higher or lower than a single stage? Someone's guessing higher. Anyone for lower? Lower. Okay, why is it lower? Use the mic, yeah.
Right now we don't have to amplify so much in one stage. We can split into two stages. So Q is smaller.
That's right. Remember, Q is related to the ratio. So that if I were to think of this as two distinct stages, I could think of stage 1 as being R high over Ri minus 1, and Q2, Q of the second matching network, as being